Ladies and gentlemen, it is my great pleasure to welcome you to the presentation Quantification of Time Domain Truncation Errors for the Reinitialization of Fractional Integrators, which I co-authored together with my colleague Rashid Malti. During this presentation, I'll start with a motivation why we should deal with fractional order system models when modeling technical applications. Afterwards, I'll give a brief overview of a generalization of a previously published exponential enclosure technique towards the use for fractional differential equations. One of the important aspects when applying this technique and also when using other solvers for fractional system models will be the quantification of temporal truncation errors. Such temporal truncation errors can be enclosed in a novel way by using an observer-based approach for a guaranteed estimation of those errors. This approach will be applied to the prediction of the state of charge of a battery model in the final part of this talk. Now, at the very beginning of this presentation, we'll have a look at two graphs. On the left-hand side, you can see the first-order time derivative of an output signal. On the right-hand side, the output signal itself. This may be on the left, a velocity of a system, and on the right-hand, the corresponding position. Now, when looking at these figures, you will notice the following aspects. These aspects are that the time responses seem to be partially faster and also partially slower than a classical exponential function. Moreover, the question arises, is it possible to explain the corresponding dynamics by a linear system model of low order, for example, a linear first or second order state space representation? Or is it really necessary to identify some nonlinear system representation? Before we coming to an answer to these questions, we take again exactly the same system model and record the corresponding frequency domain responses. On the left-hand side, the amplitude response. On the right-hand side, the corresponding phase response. Now, what you're noticing on this is, on the left-hand side, for example, the amplitude response does not only have multiples of plus minus 20 decibels of variation in the magnitude per frequency decade, but also something in between, something close to a variation of minus 10 decibels per frequency decade here in the low frequency range. Now the question is this a linear system model that we have? Obviously, it contradicts the classical amplitude variations of plus minus 20 decibels for a frequency decade. And it also contradicts the classical phase variations with the characteristic points of minus 90 degrees and minus 180 degrees, if this was a second order system model. When going back to the previous slide, here you can directly notice also a characteristic frequency at that point, which corresponds to a phase of minus 54 degrees. Again, how to approximate this system model? Is it necessary in this case to try to perform some kind of series expansion of the amplitude and phase responses by combining multiple classical first and second order transfer function blocks? And the answer is no. The corresponding system model that you see here on this slide is a differential equation that is linear. It contains the output signal y, the classical second order time derivative of the output, something like the acceleration in a mechanical system, and here in blue, a time derivative of order 0.6 of the system output. U is the external input, the system excitation. Okay, what does this non-integer order derivative of order 0.6 mean? For example, in a mechanical system, this could be an effect that lies between Newton's law, which contains a first order time derivative of the strain, which is proportional to the displacement, and Hooke's law, which is a relation that describes proportionality between stress and strain, where E is the modulus of elasticity. Now, the fractional order system model is something that is describing physical phenomena in between Newton's and Hooke's law, for example, in a mechanical application. Further scenarios where fractional system models naturally come into play are, for example, modeling electrochemical energy storage, like batteries. For that purpose, one typically uses techniques for impedance spectroscopy. One applies harmonic electric currents, IT, at the terminal of a battery, and records the corresponding magnitude and phase responses. Here, for different temperatures, you can see in each of these black, red, and blue curves that the corresponding amplitude variations, like in the scenario before, do not correspond to classical variations of integer multiples of plus minus 20 decibels for frequency decay. Also, the phase variations contradict the classical integer order system representation. Now, what is possible on the one hand is to use equivalent circuit representations with multiple RC submodels, those submodels where we have parallel connections of capacitors and resistors, and use multiples of those subcircuits in order to approximate the corresponding magnitude and phase response over some desired bandwidth. On the other hand, one could also replace the corresponding capacitors by constant phase elements. Those constant phase elements are fractional order generalizations of those capacitors, and the corresponding equivalent circuit looks the same as before, but the corresponding frequency response is being described by this numerator and denominator polynomial, where nu is now a fractional derivative order from the open interval between 0 and 1. And in such a way, we can easily try to successfully approximate the corresponding magnitude and phase responses of such systems. Now, when we are trying to simulate system models with uncertainty, one thinks of ordinary differential equations where uncertain initial conditions are given by this interval representation, where x underlined is the corresponding guaranteed lower interval bound and x overlined the corresponding guaranteed upper interval bound for the initial condition at the point of time t equal to 0. The corresponding solution to such initial value problems can be performed with multiple integration techniques, for example, V node LP, or one could also use the corresponding exponential enclosure technique, which I developed together with my colleague Katja Auer a few years ago. Now, is it possible to generalize such simulation techniques also to the fractional case? Now, we're having a closer look at the exponential enclosure technique because I think that's quite inspiring in this case. In the exponential enclosure technique, we're describing solution tubes by exponential functions, where the parameter matrix capital lambda is a diagonal matrix with intervals on its diagonal. Those intervals on the diagonal can be computed by an iteration procedure, that is based on the Picard iteration formula. And what you can see here on the slide is the corresponding iteration formula converges if the parameter interval lambda at the iteration step kappa plus 1 is a guaranteed subinterval of the parameter interval lambda at the preceding iteration step kappa. If the iteration has converged, we can compute guaranteed state enclosures at some future point capital T by just plugging in the corresponding computed parameter intervals lambda in the definition of the solution tube and taking into account the corresponding interval valued initial conditions. Now the question is it possible to generalize the procedure from the previous slide also to the fractional case? Now let's start with a scenario where the complete path of the pseudo-state of a fractional system from the point of time t equal to 0 and all points of time before this point t equal to 0 are temporarily constant and correspond to the initial condition x0. In such cases, the corresponding solution of the fractional differential equation, this is due to the corresponding initial conditions that I just explained, a fractional differential equation of Caputo type, can be computed in a closed form. The closed form solution in this case depends on the so-called Mittag-Leffler function. The Mittag-Leffler function, capital E, is described by the series representation that you can see in the lower part of the slide, where nu is again the fractional derivative order, and capital gamma is the corresponding gamma function. Now, one question still is interesting to us. What is happening if we're replacing nu with the integer value equal to 1? In this case, and that's the first note on the slide, the Mittag-Leffler function becomes exactly equal to the exponential function. That means the solution procedure for fractional differential equations becomes, in this case, for nu equal to 1, exactly the same as the exponential enclosure technique. Now, the other question is, if nu is less than 1, the infinite memory property of fractional differential equations comes into play. And that means we have to be very careful when, for example, performing a subdivision of the integration time horizon in such a way that we're computing for shorter subslices from tk till tk plus 1, for example, the solution, and that we want to reinitialize the integrator for the fractional differential equation at the point tk plus 1. When we're just ignoring the past, this obviously will lead to quite large truncation errors. Before we're coming to the quantification of these truncation errors, we're just having a look at the generalization of the exponential enclosure technique. I did already mentioned that the motivation will be replace all occurrences of the exponential function by the Mittag-Leffler function expression. We're computing again a parameter matrix lambda, which is purely diagonal and contains interval entries on the diagonal. And using a fixed point iteration based on the Picard iteration formula, we can compute again the corresponding solution parameters lambda I. A detailed derivation of this fixed point iteration was provided, for example, in those papers here published in Acta Cybernetica and also at the European Control Conference in 2020. Especially in the European Control Conference paper, we also discussed interval extensions of Mittag-Leffler functions, where we take into account specific monotonicity properties of the Mittag-Leffler function in order to evaluate this expression with small overestimation, which arises, for example, due to multiple occurrences of common interval variables. Now, I already mentioned that temporal truncation errors play a very major role when restarting the integration of a fractional system model. And a possibility for quantifying temporal truncation errors when shifting the initial point of time at which constant past of the evolution of the pseudo-state of a fractional system model was described to some future point of time, tk plus capital T. Such quantification of the temporal truncation errors can be performed, for example, by the approach published by Podlubny a few decades ago. The corresponding guaranteed bounds are described by the vector mu, and this vector is a constant vector for all future points of time, starting at the point tk plus capital T for the complete future evaluation of the state trajectory. If we are taking into account this expression for temporal truncation errors, we can reinitialize an integrator that was originally initialized at the point of time tk, for example, the point t equal to 0, and we can shift the initialization point of time to this future point of time tk plus capital T by just adding the corresponding interval bounds, which are temporarily constant, to the right-hand side of the original system model, and use this augmented system model for integrating the corresponding fractional system equations. Now, what you can obviously see is, due to the fact that these given bounds are temporarily constant, they're prone to be conservative, and this is something we want to tackle in the remainder of this talk. Before we're coming to handling temporarily variable bounds for the truncation errors, we're having a look at this graph. On the left-hand side, you can see in black the exact solution to the fractional differential equation, where on the left-hand side we have the derivative of order 0.5 of the state evolution x, and on the right-hand side of the differential equation is just equal to minus x. We're assuming that the initial condition of the system is x equal to 1, and the complete path before t equal to 0 was also the constant value x equal to 1. When we're computing the corresponding exact solution, we're ending up with the black line. And now we're naively integrating, for example, in the red curve from t equal to 0 till the point t equal to 1. And now we're restarting the integration and ignoring the fact that the past was not constant. And we're just replacing the initial condition by this red dot. And what you will see then afterwards is that the corresponding solution deviates significantly from the exact solution. And this is getting worse and worse after each reinitialization. And the same phenomenon and even larger approximation errors occur when we're reducing the corresponding integration step size, for example, from delta t equal to 1 to delta t equal to 0.1. We can solve this problem by using the corresponding guaranteed constant error bounds mu from the previous slides. And in such a way, we will end up with interval enclosures here in gray that contain the exact solution. For example, for nonlinear system models, one can effectively use such error bounds to reduce the width of the corresponding computed interval enclosures. In blue, you see the bounds that are obtained by determining one constant enclosure parameter lambda for the complete integration time horizon from t equal to 0 to t equal to 1. And in red and in yellow, you can see integration results for shorter time horizons. If we restart the integration here in the yellow and in the red scenarios and take into account the guaranteed bounds mu from the previous slides, we can see that the corresponding solution tubes become tighter than the one that was obtained for initially long integration time horizon. And this is the benefit of some step size control strategies for integrating fractional system models while taking into account the effect of truncation errors in a guaranteed way, still with constant error bounds. Now the question is it possible to use information from the simulation of a fractional system model, on the one hand initialized at t equal to 0, for the reinitialization at some future point of time? For that purpose, we restrict ourselves in the remainder of this talk to the case that we have cooperative dynamic system models. And this cooperative dynamic system model is described as in such a way that we can compute guaranteed bounds for the pseudo-states X in such a way that the lower bounds are denoted by V and the upper bounds are denoted by W. We have corresponding bounding systems, and if we assume that the initial condition was specified at the point of time t equal to 0 and that it was temporarily constant for the complete past, the corresponding lower bounds x0 underlined and the upper bound x0 overlined will be the initial condition here at the point v at t equal to 0 and w at t equal to 0. Now let's assume that we have integrated the system model till the point of time capital T, which is greater than 0. And at this point of time, we can derive constant guaranteed error bounds for the truncation error by Podlubny's formula. These are now the bounds minus mu t and plus mu t for each of the component of the pseudo-state vector. Now we are augmenting our system model. We do not only take into account for the bounding systems FV and FW from the previous slide, but we add two integrated disturbance models with the right-hand side equal to 0, which describe the temporal evolution of lower and upper bounds for these truncation errors. Now, due to the fact that we have already some information V and W for the original integration of the system model initialized at t equal to 0, we can design something like a Lünberger type state observer that is well known from control theory. And the only thing that we have to choose now is an observer gain matrix H, which on the one hand side makes sure that the error dynamics, that means the deviation between the so-called measured variables v and w, and the new estimates v tilde and w tilde are asymptotically stable. And on the other hand, we want to find a parameterization h in such a way that v tilde and w tilde are something like guaranteed outer bounds for the true state evolution. That means something like an interval observer or a framer for the true system dynamics. And the initialization of the state vector at the point of time t equal to capital T corresponds to the simulated results at the point of time and the corresponding constant error bounds by Podlubny's formula. And now what we are using this approach for is to periodically reset fractional integrators when simulating differential equation models. And this forms also the basis for implementing predictor corrector type state estimation schemes where we have continuous time dynamics for the system model, but only discrete time measurements. Now let's come to some examples. First of all, again, an academic example. On the left-hand side, you can see the true state evolution here by the black bounds, by the blue bounds, the upper and the lower bound. And when resetting naively, as just described on the previous slide, with constant error bounds, mu t, the integration, you will see in the red bounds. Now, applying the observer-based enhancement from the previous slide, you can already see that the bounds are tightening. Tightening can even become better if we have enhanced information at the resetting points about the state variables. These are either resetting, in the case of constant error bounds, to the true solution results, or on the right-hand side, the same thing for the observer-based enhancement. And especially on the right side, you see that resetting allows us to obtain very close results that are more or less the same as the simulation without any reset of the fractional integrator. Why is such resetting interesting? As I already mentioned, predictor corrector type state estimators usually have at those sampling points information about the system states. For example, we take into account those interval valued uncertain measured quantities, the measured system outputs. Those can serve as the resetting quantities, and the solution enclosures even get tighter than the original blue bounds. Now let's apply this to the simplified battery model that we discussed at the very beginning of this talk. We have now a three-component state vector of pseudo-states. This is the state of charge sigma, its fractional derivative of order 0.5, and the voltage V1 over the corresponding constant phase element. The terminal voltage of the battery can serve as a measured quantity, and the terminal voltage is described by this nonlinear expression here, depending on the state of charge sigma. And the corresponding system and input matrices, input matrix, input vector B, are described by those equations here. We are assuming now that we're simulating a controlled discharge of the battery. After performing some pole assignment procedure, we have computed the controller gains small k. When applying the Mittag-Leffler-Type state enclosures for this non-cooperative system parameterization, we end up with enclosures for the state of charge and also for the terminal voltage of the battery. On the other hand, we can also use, after a slight modification of the parameters, in order to end up with a cooperative system model, we can use also the observer-based quantification scheme from the truncation errors. In this case, we are using an uncertain system matrix AC. Using this matrix, we have designed bounding systems for the worst case upper and lower state boundaries. And this terminal voltage here in the last line of the slide serves again as some measured quantity on the following. Now let's have a look at a naive simulation of the system when resetting after 1 minute of simulation time the fractional integrator and take into account constant error bounds mu. In this case, you see that for the state of charge x1, for the second state x2, and also for the third state x3, the bounds are blowing up here in red, while exact, the true bounds will stay here in blue in the interior and converge to some corresponding steady state. Now, when resetting the corresponding fractional integrator and taking into account the information at those sampling points after 1 minute, after 2 minutes, and so on, we can see that already the corresponding enclosures are getting much tighter. The red ones are much better than we had seen before. On the right-hand side, at the moment, you cannot even see a difference between the simulation without reset and reset. That's the reason because we have performed here something like a contractor-based observer. We have assumed that with some small interval uncertainty, the terminal voltage is measurable. We have reconstructed all 3 system states, X1, X2, and X3 at those sampling points and restarted the temporal integration. The small errors at these restarting points here can be seen in the zoomed in version. In the zoomed in version, you can see those small peaks here for the first, second, and also third state variable, and the corresponding bounds are more or less the same as the simulation of the exact system dynamics. Now let's come to conclusions and an outlook on future work. What you have seen in this presentation is interval techniques can be applied for verified simulation of fractional differential equations. They're readily applicable for predictive control purposes, system identification and state estimation. We can especially handle uncertainty in initial conditions and parameters. And the novel feature of this talk is we are able to handle time domain truncation errors when resetting fractional integrators. And this allows us to implement predictor corrector state estimation schemes, which will be developed further in future work and also enhanced towards nonlinear output functions. And especially what we want to perform is parameter identification, which can be parallelized on a GPU in a quite cheap manner, and also identify bounds on the initialization function for a finitely long past window of time. Thank you very much for your attention. On this slide, you can see a few related publications concerning this topic that I just presented. Thank you very much.